The thing sitting in your pocket right now has more history soaked into it than most countries do. And I mean that literally. The material inside your phone battery, the compound in millions of psychiatric prescriptions, the alloy holding together the wing of the plane you last flew on, all of it traces back to one element. One that most people think they understand. One that most people are completely wrong about. I want you to stop for a second and think about what you actually know about this element. Go ahead. Take a mental inventory. Batteries, right. Maybe something about mood medication. Perhaps you have heard it floats on water. Maybe you have heard it is mined somewhere in South America and that the process is not exactly gentle on the environment. That is usually where the knowledge stops. And I get it, because that is where most articles stop too. That is where most videos stop. That is where the 2 sentences in the textbook end. But here is the thing that got me when I started seriously pulling on this thread. Every single one of those facts, the batteries, the medication, the mining, every single one of them is the surface of something that goes so much deeper that when you actually look at it, it changes how you think about progress itself, not in an abstract way, in a very specific, very uncomfortable, very human way. This element has been sold in a fizzy drink. It has been the active ingredient in a thermonuclear device. It has kept people alive who would otherwise not have survived their own mines. It has poisoned rivers. It has been banned by governments and then quietly reinstated when the same governments realized they could not build the future without it. It has been the waste product of a weapons program that later became the key material for clean energy research. The same substance, different decades, wildly different intentions. And here is what really got under my skin when I spent months going through the actual history of this thing. Almost none of it was planned. No one sat down with a clean sheet of paper and said, "Right, let us take element number 3 and build a civilization around it." It happened through accidents, through wrong guesses that turned into right answers, through discoveries that were ignored for a decade because they came from the wrong person in the wrong place, through catastrophes that set the whole story back by years and then quietly pushed it forward again. I kept coming back to one question while I was putting this together. How does something this small, 3 protons, 1 electron available to bond with whatever it meets, how does something this structurally simple end up woven into so many completely different parts of human life? Medicine, warfare, aviation, psychiatry, energy, geology, even your morning coffee mug might have trace amounts of it in the ceramic. That is not a metaphor. That is a real possibility depending on how the clay was fired. So when people ask me, "Yeah, but why does this element matter?" I want to say, because it is already everywhere you have not thought to look. And because the story of how it got there is one of the most genuinely strange journeys any material has ever taken through human history. We are going to go all the way back. Not to the first lab that identified it, not to the first person who named it. Further back than that. Much further. Because where this element actually comes from is the first thing that should stop you cold. And it will. Friends, if you find this kind of storytelling interesting, subscribe and leave a like. It genuinely helps this channel keep going and means we can keep digging into stories like this one. So let me tell you what this channel is actually trying to do, because I think it matters to say it out loud before we go any further. There is a version of science communication that I find almost physically painful to sit through. It is the version where everything is clean and inevitable. Where the discovery happens, the scientist has a brilliant insight, the world recognizes its importance, and progress marches forward on a straight line. I understand why that version exists. It is easier to tell. It is easier to absorb. It fits into a school curriculum without making anyone uncomfortable. But it is not what actually happened. Almost ever. What actually happened, across pretty much every major discovery I have spent serious time researching, is messier, stranger, and honestly more interesting than the clean version. The right answer gets buried because the wrong person found it. The useful substance gets banned because someone else misused a related compound. The technology that changes everything sits in a drawer for 15 years because the economic incentive was not there yet. The person who eventually makes it work is not the one who gets the credit. That gap between the clean version and the real version is what this channel exists to close. Not because I want to make science look bad. The opposite. I think the real version is more compelling than anything you could make up. I think the real version, with all its wrong turns and ignored breakthroughs and accidental discoveries and tragic timing, I think that version actually makes you trust the process more, not less. Because it is honest about what the process costs. And the element we are starting with today is a perfect entry point for exactly that kind of story. Because it has been through everything. It has been adored and feared and banned and weaponized and redeemed, sometimes within a single generation. It has been understood correctly, then misapplied catastrophically, then avoided out of that same fear, then slowly, painstakingly brought back into legitimate use by people who refuse to let a bad chapter close the whole book. Every time I think I have found the most surprising part of its history, I find something underneath it. There is a layer where it is a consumer product sold to families as a health tonic. Below that, a layer where it is a controlled substance in a psychiatric ward. Below that, a classified material in a Cold War facility. Below that, a cosmological mystery that the best physicists alive have not resolved. And below all of that, something even older and stranger that we will get to in a moment. That is the kind of story this is. Not a list of facts arranged in order. A story where each answer opens two more questions. Where the timeline is not a straight line, but something that doubles back on itself. Where the same substance that harmed people in one decade became the thing that kept other people alive in the next. I am not here to make you feel good about progress. I'm not here to make you feel bad about it either. I am here to show you what it actually looks like from the inside. And what it looks like, if you are paying attention, is nothing like the version you were taught. So let us start at the very beginning. And I mean the very beginning. This element did not come from a star. Let that land for a second, because it sounds like a small detail, and it is actually one of the strangest facts in all of physics. Every metal you have ever touched, iron, copper, gold, silver, the aluminum in your kitchen, all of it was forged inside a star. A massive, burning, ancient star that eventually collapsed or exploded and scattered its contents across space, where those atoms drifted for millions of years until gravity pulled them together into new planets, new rocks, new mountains. That is the standard origin story for the elements that built the physical world around you. This element skipped that entire process. It did not wait for a star. It did not need one. It formed before stars existed, in the first few minutes after the universe itself began, when all of space was so hot and so dense that nuclear reactions were happening everywhere at once, with no container, no core, no furnace to host them. Just raw energy converting into matter, and matter colliding and fusing at temperatures we do not have useful comparisons for. The process lasted a few minutes. Then the universe cooled just enough that it stopped. And in those few minutes, three things were produced in meaningful quantities: hydrogen, which became almost everything; helium, which became most of the rest. And this element, in amounts so small that one atom for every 10 billion hydrogen atoms, is actually considered significant by the physicists who study this period. 1 atom per 10 billion. I want you to sit with that ratio for a moment, not as an abstract number, but as a physical reality. Imagine a stadium packed with 10 billion people. Now imagine one person in that stadium is made of something fundamentally different from everyone else. That is the concentration we are talking about. That is how rare this element was in the early universe. And yet somehow, over billions of years, gravity did its slow and patient work. Those trace amounts concentrated into rocks and mineral veins and ancient underground brines. And eventually a junior chemist in a cold northern lab broke open the right mineral at the right moment and found it sitting there, waiting. But here is the part that really stopped me when I first read about it properly. The story of this element does not just start at the beginning of the universe. In a very specific and unsettling way, it starts with a question the universe has not yet answered about itself. When you trace how this element formed in those first few minutes, the physics is precise. The equations that describe what happened in the early universe are some of the most tested and verified in all of science. They predict, with remarkable confidence, exactly how much of each element should have been produced. The numbers for hydrogen and helium check out almost perfectly when you measure what is actually out there. But when researchers point instruments at the oldest stars in existence, the ones that formed from that original primordial material before anything else mixed into the picture, the amount of this element they find is consistently, stubbornly, about 3 times lower than the equations say it should be. 3 times lower. Not a rounding error, not instrument noise. A real, persistent, reproducible gap between what the math predicts and what the universe actually shows. And nobody has solved it. I want to be clear about what that means, because it is easy to hear something like that and feel like the ground is shifting under you. It does not mean the physics is wrong. It does not mean the story of the early universe is broken. What it means is that somewhere between the theory and the measurement, something is happening that we have not fully accounted for yet. Maybe the element gets destroyed inside certain types of stars before we can measure it. Maybe there are interaction processes that are not yet in the models. Maybe the oldest stars are not quite as pristine and uncontaminated as the method assumes. All of these are serious, active hypotheses being worked on by serious people right now. But none of them has been confirmed. The gap is still there. Open. Named. The cosmological lithium problem. An official, documented, unresolved question sitting right at the foundation of our best model of how everything began. And here is what I find genuinely remarkable about that. Not unsettling, remarkable. The fact that the gap has a name means someone found it. The fact that it is published and debated means science did not hide it. The model is precise enough to notice its own inconsistency. That is not a sign of weakness. That is what a good instrument does. It tells you when something does not add up, even when that something is inconvenient, even when fixing it means rethinking assumptions that have been comfortable for decades. Most systems, human systems anyway, do not work like that. Most systems paper over the gaps and hope no one measures carefully enough to notice. Science at its best does the opposite. It measures carefully, finds the gap, gives it a name, and keeps working. That quality, the willingness to sit with an open question without pretending it is closed, turns out to be exactly what the human story of this element is missing at its most critical moments. Because when you follow what happened after it was discovered on Earth, what you find is a long and painful pattern of people deciding they understood something they did not, acting on that incomplete understanding, and leaving other people to pay the price. The universe left a gap in its own story and kept going. Humans found this element, assumed they had it figured out, and caused real harm. The contrast is not subtle, and it starts almost immediately after the first person broke open that mineral and realized something new was inside. The man who found this element was not looking for it. That is the first thing you need to know. He was not on some grand expedition, not chasing a theory, not funded by anyone with a vision. He was a young assistant doing exactly what young assistants do, grinding through routine analytical work in someone else's laboratory, checking mineral samples one by one, recording results in a ledger that probably nobody else ever read. His name was Thomas Allard, and on an ordinary morning in a cold stone building in northern Europe, he cracked open a sample pulled from a remote coastal island and found something that did not fit any category he had been trained to recognize. The mineral itself was unremarkable to look at, grey, dense, slightly waxy on the fractured surface. It smelled faintly of dust and cold rock, the way all mineral samples do when you split them open, that dry mineral smell that coats the back of your throat. Allard dissolved it, ran his standard tests, and kept getting results that made no sense. The material behaved like the alkali metals he knew, like sodium and potassium, but the numbers were wrong. It was lighter than either of them. It burned with a color he had not seen before. It reacted differently to every test he ran, not in a way that suggested contamination or error, but in a way that consistently pointed to something genuinely new. He brought the results to his supervisor, a well-established chemist named Dr. Harwick, who had built his career on systematic rigor and was not the kind of man who got excited easily. Harwick looked at the data, looked at Allard, looked at the data again, and then did something that surprised the younger man. He smiled. Not a big smile, a careful, contained smile, the kind that means, "I think we have something here, but I'm not going to say that out loud until I am certain." Harwick proposed the name. He reached back into ancient Greek to the word for stone, because this new element had come from rock rather than from the plant ash that had yielded its nearest chemical relatives. It was a quiet, almost philosophical naming choice. Most elements at that time were named after places or after their physical properties. This one was named for the simple fact of where it lived, in stone, waiting. But here is where the story takes its first unexpected turn, because naming something and actually holding it are very different things. Allard and Harwick could identify the element in the mineral. They could measure its properties indirectly. What they could not do was isolated. Every attempt to pull pure material out of the compound ended with the sample reacting violently with whatever it touched: the air, the moisture in the air, the glass container. It was like trying to catch smoke with bare hands. You could see it, you could describe it, but the moment you reached for it, it was already doing something else. Pure isolation came from a different researcher entirely, years later, working in a different country, using a technique that had not existed when Allard first cracked open that grey mineral. The method involved running electrical current through a molten compound until the element separated out as a tiny bead of silver metal. The researcher described it afterward as almost anticlimactic. After all the theoretical groundwork, after all the indirect measurements and careful predictions, the actual metal sat there on the ceramic dish looking soft and unremarkable, already beginning to cloud over at the edges where it met the air. Beautiful for about 30 seconds. Then chemistry took over. And that is the thing about this element that I kept coming back to as I dug through all of this. It exists at the edge of stability. It wants to react. It is, at a molecular level, almost restless, always ready to give away its single outer electron to whatever is nearest. That quality, that eagerness to bond and transform, is what makes it so extraordinarily useful across so many different applications. But it also means you can never quite hold it still. You can never fully contain it. Every use of this element, in every industry and every era, involves engineering around that fundamental restlessness rather than eliminating it. The first people who handled pure samples quickly learned that the standard rules did not apply. You could not store it in water. You could not leave it in open air. You needed mineral oil, sealed glass, controlled environments. For a material that would eventually end up inside billions of consumer devices, it had an almost aristocratic intolerance for ordinary conditions. What nobody understood yet, standing in that cold lab, watching the tiny silver bead turn grey at its edges, was that this restlessness was not a flaw. It was the whole point. Every property that would make this element central to aviation, to psychiatry, to energy storage, to weapons design, every single one of those properties flows directly from that same eagerness to let go of its outer electron, to bond, to transform, to react. The lightness, the electrochemical potential, the way it moves through certain materials almost without resistance. All of it comes from the same source. But lightness needs to be explained properly, because when I say this is the lightest metal on Earth, I do not just mean it is slightly less heavy than the others. I mean it is in a completely different category. Drop a piece of this metal into a glass of water, and it does not sink. It floats. And while it floats, it reacts, fizzing and warming the water around it, generating gas, moving in slow circles driven by the bubbles coming off its surface. It is the only metal you will ever see doing that. Not just floating, but floating while actively transforming the liquid beneath it. There is something almost alive about it when you watch it happen. Something that makes the back of your brain register a small alarm, because metals are not supposed to behave this way. Metals sink. Metals are cold and still and heavy. This one does none of those things. Its density is roughly half that of water. To put that in terms you can feel, a block of this metal the size of a brick would be lighter than most hardcover books. A sphere of it, the size of a baseball, would sit comfortably in your palm without your wrist noticing the weight. That is not a metaphor. That is the actual physical reality of the lightest solid metal on the periodic table. And that lightness has consequences that ripple through every chapter of this story. It is why the element ends up in aircraft frames, saving hundreds of kilograms per plane and translating directly into fuel savings across decades of service. It is why it works as a battery material, because the lightest ion moves fastest and stores energy most efficiently per unit of weight. It is why it was so attractive to weapons designers who needed the most energetic reactions possible from the smallest possible mass. Lightness is not a neutral property. In engineering terms, lightness is power. But here is what nobody tells you in the standard summary of this element. That same lightness, that same electrochemical eagerness, creates a problem that haunted every person who ever tried to use it. The gap between a useful amount and a harmful amount is dangerously narrow. What helps in small quantities can cause real damage in larger ones. And in the early years, when nobody had properly mapped that boundary, when the element was being celebrated and sold and consumed with almost no oversight, people paid for that ignorance in ways that should have been preventable. And that chapter of the story is darker than almost anything that comes before it. For decades, this element was sold in a bottle with a cheerful label, marketed to families as something that would improve their mood, and the company doing it knew exactly what was in the product and advertised it proudly. This was not a secret ingredient. It was the selling point. The label said it. The newspaper ads said it. The salesman said it to grocery store owners while stacking cases on the shelf. Come try our drink. It has got the special compound that lifts your spirits and clears your head after a rough night. And people bought it. Millions of them, for nearly 2 decades. Let me paint you the picture of how this happened, because it did not come from nowhere. By the time that drink hit the market, this element already had a reputation in certain circles as something with wellness properties. Not fringe circles either. Medical circles. Physicians had been experimenting with lithium salts since the mid-1800s, and while the science behind those experiments was loose by any modern standard, the observations were real enough to build a reputation on. Some patients who received lithium compounds reported feeling calmer, clearer, more stable. Word traveled the way medical word always traveled in that era, through journals, through conferences, through one doctor writing a letter to another doctor he trusted. So when the consumer market started looking for the next big tonic, the next product that could claim a health benefit and actually have some vague basis for that claim, lithium was sitting right there. Respectable enough to cite, vague enough to market broadly, and cheap enough to put in a fizzy drink and still turn a profit. The drink launched with lithium citrate in the formula. Not hidden, not disguised, right there in the product identity. The marketing positioned it as a mood balancer, something that took the edge off a hard day, smoothed out the rough mornings, gave you a kind of chemical steadiness that coffee could not. The language was careful enough to avoid making outright medical claims, but pointed enough that everyone understood what was being implied. This drink will make you feel better. This drink has something in it that works. And here is the genuinely strange part. It probably did work. At least a little, at least for some people. Lithium citrate in small amounts has a mild effect on certain neurological pathways. Not a dramatic effect, not a therapeutic effect in any clinical sense, but enough of an effect that a person paying attention to their own mood might notice something. Combined with the power of expectation, with the simple pleasure of a cold carbonated drink on a warm afternoon, with the social ritual of cracking one open after work, the product delivered enough of a feeling to keep people coming back. The drink sold well for years. It went through name changes, formula tweaks, branding updates. The lithium stayed in the formula through all of it. Families kept cases of it in the kitchen. Doctors did not object, because the doses were low and the complaints were few, and the general medical consensus was still that lithium in modest amounts was more or less harmless. The company was not lying, exactly. It was doing what consumer companies have always done, finding a property that sounds credible, amplifying it beyond what the evidence actually supports, and selling it as a lifestyle product. Then the regulators caught up. Not dramatically, not with headlines, but quietly, the way regulatory decisions usually happen. The compound was pulled from the formula. The drink continued under a name it still carries today, stripped of its original active ingredient, existing now as just another flavored soda with no idea, on most of its consumers' part, of what it used to contain. I find something almost melancholy about that. Not because I think people should still be drinking lithium in their sodas, obviously not. But because it captures something true about how this element kept getting used before anyone fully understood it. Reach for the benefit, ignore the complexity, sell the feeling. The problems come later, and someone else deals with them. And the problems did come, but to understand them properly, you need to understand where the medical idea behind all of this actually originated, because it goes back much further than a fizzy drink, and it is considerably more interesting than a marketing campaign. The theory that put lithium on the medical map in the first place came from a pattern that 19th century physicians kept noticing and could not explain. Certain patients who suffered from painful joint inflammation, the kind that settled into the toes and ankles and made walking feel like pressing bare feet onto broken glass, those same patients seemed to experience unusual swings in their mental state. Periods of agitation and restlessness, followed by periods of deep, flat withdrawal. The two conditions appeared together often enough that doctors started looking for a shared cause. The hypothesis they landed on was not insane, given what was understood at the time. They proposed that a buildup of certain waste compounds in the body was responsible for both conditions. The logic was that when those compounds accumulated in the joints, you got inflammation and pain. When they reached the brain somehow, you got the mental symptoms. One root cause, two expressions. Clean, symmetrical, satisfying in the way that simple explanations always are. And then someone noticed that lithium salts dissolved those waste compounds in a laboratory dish better than almost anything else available. The crystals would sit in solution, opaque and stubborn, and then the lithium compound would go in and within minutes the solution would clear. You could watch it happen. That visual proof, a dish full of dissolved crystals, was enormously persuasive to physicians who were used to working from observation rather than controlled trials. So they started giving lithium to patients. Not in any standardized way, not with any systematic tracking of outcomes, but in the rough empirical tradition of 19th century medicine, which was essentially this. Try it on a few people, watch what happens, and if more of them seem better than worse, keep doing it. A physician named Dr. Ellsworth, working out of a small practice in a mid-sized city, became one of the more vocal proponents of this approach. He documented cases. He wrote letters. He presented at local medical gatherings. He was not a famous man, not a groundbreaking researcher, just a careful observer who was convinced he was seeing something real. Some of his patients did improve. Others saw no change. A few reported side effects that Ellsworth noted carefully but did not know how to interpret. The honest answer was that nobody at that point had the tools to run the kind of study that would separate real therapeutic effect from the enormous power of expectation and attention. When a doctor believes in a treatment and communicates that belief to a patient, the patient often improves somewhat regardless of what the treatment actually does. That mechanism was not understood or accounted for in Ellsworth's era. What this meant in practice was that lithium accumulated a medical reputation that was partly real and partly artifact, a mixture of genuine effect and genuine noise that nobody could yet separate. And that mixture, that reputation built on incomplete evidence and honest enthusiasm, is what eventually made its way into the soda bottles and the health tonic advertisements. The drink manufacturers did not invent the idea that lithium was beneficial. They borrowed it from medicine. And medicine had borrowed it from a hypothesis about joint inflammation that was itself only partially correct. This is how bad ideas travel through institutions that are supposed to know better. Not through dishonesty, most of the time, through the slow accumulation of stories that feel like evidence, through the human need to have an explanation, through the gap between what we observe and what we can actually prove. By the time anyone thought to run a rigorous test, lithium already had a reputation that felt too solid to question. And that feeling of solidity was about to cause serious damage. People were buying lithium at the grocery store, shaking it onto their food like table salt, and nobody stopped them because nobody thought they needed to. That is the part that still gets me when I sit with this chapter of the story. The element that had spent decades accumulating a medical reputation, the one that had traveled from physician letters to health tonic advertisements to fizzy drink labels, eventually landed in a small cardboard box on a supermarket shelf next to the regular sort, positioned as a safe substitute for people whose doctors had told them to cut their sodium intake. No prescription, no dosing guidance, no warning label about what happened if you used too much. Just a box. Just a product. Just the quiet assumption that if it was on the shelf, someone responsible had already checked. They had not checked. Not carefully enough. The logic that put it there was not completely irrational. Certain lithium compounds do not contain sodium, and patients with specific heart conditions were being told by their doctors to reduce sodium dramatically. The market saw a gap. Someone filled it. The product was real. The need was real. And the early feedback was fine because most people used it in normal amounts and felt no different from before. The problem was the people who did not use it in normal amounts. Here is the thing about this element that keeps appearing throughout its entire history in every single context. The gap between a helpful dose and a harmful one is unusually narrow. Most substances have a wide margin. You could take twice the recommended amount and feel fine, maybe just a headache. With this element, that margin collapses. What helps at one level causes real neurological damage at a higher level, and the symptoms of too much look nothing like what you would expect from something you shook onto your scrambled eggs. Trembling hands, confusion, a strange, heavy feeling in the limbs like your body is trying to move through deep water. In severe cases, much worse. People who were already unwell, whose kidneys were not processing compounds efficiently, whose bodies could not clear the accumulation fast enough, those people crossed the line without knowing a line existed. Some were hospitalized. Some did not recover fully. A small number did not recover at all. The regulatory response was swift once the pattern became visible. Lithium compounds were pulled from general sale. Medical use was placed under strict controls. And then something happened that had nothing to do with logic and everything to do with how institutions process fear. The restrictions did not stop at the grocery store shelf. They effectively froze the entire medical conversation around this element. The reasonable response, tighten the controls on unregulated consumer use, became an unreasonable one. Treat the element itself as categorically dangerous and close the door on clinical research. That door closed at almost the exact moment it should have been swinging wide open. Because on the other side of the world, in a country that had nothing to do with the supermarket scandal, a psychiatrist was sitting in a converted storage room with a notebook full of observations that would eventually change everything. And he had no idea that the door had just been slammed in his direction. His name was Dr. Marcus Webb, and he worked at a regional psychiatric facility in a city that most of the medical world had never heard of and had no reason to think about. The facility was underfunded in the way that psychiatric facilities in that era were almost universally underfunded, which is to say profoundly, structurally, and without apology. The wards were full. The staff were stretched. The treatments available were limited to options that worked poorly, caused significant harm, or both. Webb had watched people arrive at his facility in states of extreme mental crisis and leave, if they left at all, essentially unchanged, because there was nothing effective to offer them. He was not a visionary. I want to be clear about that because the way these stories usually get told, the lone researcher becomes a heroic figure standing against the establishment, and that framing flattens what actually happened. Webb was a practical man with a practical problem. His patients were suffering in ways that the available tools could not address, and he refused to accept that as a permanent condition. So he started experimenting with what he had, which was almost nothing. The room he used as a workspace smelled like disinfectant and old wood, the same institutional smell that soaked into every corner of the building. He kept his notes in a battered ledger with a cracked spine. His equipment was minimal, borrowed or repurposed from other parts of the facility. He was not running a laboratory. He was running a series of careful observations with whatever materials he could access, driven by a question he could not let go of. Was there something in the biological chemistry of his most severely affected patients that he could identify, and if he could identify it, could he interfere with it in a useful way? He started with his worst case. A man named Gerald, who had been in the facility for years, whose condition had not improved with anything that had been tried, who spent most of his days in a state of agitation so continuous that the staff had come to think of it as simply his baseline. Gerald was loud in the way that profound internal distress makes people loud, not aggressive, just relentlessly present, unable to rest, unable to quiet the thing that was running in him constantly. He had not slept a full night in longer than anyone on the ward could remember. He had lost significant weight because eating required a stillness he could not achieve. He was, by any honest assessment, running on empty in a body that was failing to refuel. Webb introduced a lithium compound into Gerald's daily routine at a carefully measured dose, lower than what the grocery store customers had been shaking onto their food, monitored at every step, adjusted based on daily observation. He sat with Gerald every morning and asked the same questions and wrote down the answers in his cracked ledger. For the first several days, nothing changed. Gerald was exactly as he had been. Webb kept the dose steady and kept taking notes. On the 5th day, Gerald slept for 4 hours. Webb found out from the night nurse, who mentioned it almost as an aside, the way you mention something small that you are not sure matters. Webb wrote it down and did not let himself feel anything about it yet. On the 8th day, Gerald slept for 6 hours and came to breakfast without being called 3 times. He sat at the table and ate most of what was in front of him. He did not speak much, but the quality of his silence was different. It was the silence of someone resting rather than the silence of someone held in place by exhaustion. By the 3rd week, Gerald was sitting in the common room in the afternoon, watching other patients, occasionally responding when spoken to. The nurse who had worked his ward the longest stood in the doorway one afternoon and watched Gerald for a long moment, and then turned to Webb and said something that Webb wrote down verbatim in his ledger because he wanted to remember exactly how it sounded. She said, "He looks like himself. Not like who he was when he came in. Like who he might have been before any of this." Webb published what he found. Not in a major journal, not with fanfare, just a careful account of his observations, the doses he had used, the timeline of changes, the outcomes for a small group of patients. He sent it to several publications. It appeared in one. And then, for reasons that had everything to do with the regulatory climate and the fear response that had followed the grocery store crisis, almost nobody responded. Webb's paper sat largely unread for years, while patients who could have been helped went without, and the people responsible for that delay never once had to look those patients in the eye. That is the sentence I kept coming back to when I was piecing this part of the story together. The work existed. The evidence existed. Gerald had walked out of that facility and gone home and stayed home for years, functioning, present, recognizably himself for the first time in longer than his family could properly remember. That outcome was documented. And it changed almost nothing immediately, because the institution that might have acted on it was still flinching from the grocery store disaster, still operating in the long shadow of a fear response that had calcified into policy. What eventually broke the silence was not a dramatic moment. It was something slower and less satisfying than that. A researcher in Northern Europe named Dr. Elsa Norgard came across Webb's published account while working through a stack of older journals that most of her colleagues had not bothered with. She almost set it aside herself. The paper was dry, the sample size was small, and it came from a facility nobody in her circle had ever cited. But something in the data held her attention. The pattern of improvement across Webb's patients was too consistent to dismiss. It did not look like placebo. It did not look like the natural fluctuation of untreated illness. It looked like a treatment working. Norgard was methodical in a way that Webb, working alone with no institutional support, had never had the resources to be. She had a team. She had funding. She had the infrastructure to design the kind of study that could separate signal from noise. She spent the better part of 3 years running controlled trials, adjusting dosages, tracking outcomes across a large enough group of patients to produce numbers that could withstand scrutiny. The work was painstaking and unglamorous, the kind of research that does not make for exciting stories because most of it is just careful people in quiet rooms checking the same measurements over and over and recording the results honestly. What she found confirmed what Webb had seen in his converted storage room, and then went further. Lithium did not just reduce the acute episodes, it prevented new ones from forming. Patients who had spent years cycling through periods of extreme agitation, followed by long stretches of flat withdrawal. Patients whose families had quietly stopped planning for any kind of stable future. Those patients on lithium stayed level for months, and then for years. Not perfectly level, not freed from every difficulty, but stable in a way that made ordinary life possible, work possible, relationships possible. Norgaard published her findings, and this time the medical world did respond, slowly, cautiously, with the institutional reluctance that follows any reversal of an established position, but it responded. Other researchers replicated the trials. Other facilities reported similar outcomes. The data accumulated in the way that good data does, one careful study at a time, each one adding a layer of confidence to the one before, until the weight of evidence became too substantial to set aside. Formal approval came eventually, years after Norgaard's first publication, years after Webb's original paper, decades after Gerald had walked out of that facility and gone back to his life. The regulatory process moved at the pace regulatory processes move at, which is to say slowly enough to be genuinely costly in human terms. Every year of delay was a year of patients cycling through episodes without access to something that could have helped them. That cost was real, and it was paid by people who never appeared in any of the official documents about the approval process. But the approval came. And what followed was something that happens only rarely in medicine. A treatment earns its position not through aggressive marketing or institutional momentum, but through the simple accumulation of results that nobody can convincingly argue with. Lithium became the standard. It held that position. Decade after decade, newer compounds arrived with promises of fewer side effects or more targeted action, and some of them delivered on those promises for some patients. But lithium stayed at the top for the most severe presentations because it kept working when other things did not. That staying power is what makes the next question so genuinely strange. And I want you to hold this question in your head for a moment before I give you the context around it, because the strangeness of it only becomes clear when you understand how unusual this situation actually is. After more than 50 years of clinical use, after tens of thousands of studies, after this element has been given to tens of millions of patients around the world, and its effects have been measured, tracked, analyzed, and published more thoroughly than almost any other psychiatric compound in history, we still do not fully understand how it works. Not in the way that scientists want to understand something. Not at the level of being able to point to a specific mechanism and say, this is the thing it does, this is why patients improve. We know what it does in broad terms. We do not know with certainty which of the many things it does is the one that matters most. Let me be specific about what that means, because it is easy to hear something like that and treat it as a minor gap, a detail left to fill in later. It is not a minor gap. It is the central question of the entire pharmacology. When a lithium compound enters the body and reaches the brain, it interacts with multiple systems simultaneously. It affects the way neurons regulate certain enzymes. It influences the balance of chemical messengers that govern mood and energy. It appears to stimulate the growth of new neural connections in regions associated with memory and emotional regulation. It seems to protect neurons from certain kinds of damage in ways that go beyond its immediate chemical interactions. Each of these effects has been confirmed in laboratory conditions. Each of them has research behind it. But when you ask which of these mechanisms is responsible for the clinical benefit, for the thing that kept Gerald stable for years after he left Webb's facility, For the thing that Norgard documented across hundreds of patients in her trials, the honest answer is that nobody knows for certain. The candidates are real. The winner has not been named. What makes this especially striking is the contrast with how medicine usually works. When a drug earns a position as the primary treatment for a serious condition, the expectation is that the mechanism is understood. That is partly how confidence in the treatment gets built. You know what it does, you know why it works, and that knowledge lets you predict how it will behave in different patients and different combinations. With lithium, that middle step, the why it works, has remained genuinely open despite everything that has been written about it. And here is what I find most thought-provoking about that. The clinical confidence in this element is enormous. The mechanistic understanding of it is incomplete. Those two things coexist without apparent contradiction because the results have been reproduced so consistently across so many different settings and populations that the uncertainty about mechanism does not reduce the confidence in outcome. It works. We use it. We keep studying why. That combination, high confidence in the effect and genuine uncertainty about the cause, is rarer in medicine than most people realize. And it raises a question that goes beyond lithium specifically. How much of what we use in medicine do we truly understand versus how much do we apply because the results hold even when the explanation is still being worked out? The answer to that question is more interesting and more unsettling than most people expect. And the story of this element is one of the clearest illustrations of it that exists anywhere in the scientific record. But here is where the story takes a turn that has nothing to do with hospitals or researchers or carefully kept ledgers. Because while psychiatry was slowly building its case for lithium through controlled trials and cautious approvals, somewhere else entirely, people in very different rooms were looking at this same element and seeing something completely unlike a medication. They were not thinking about what it could stabilize. They were thinking about what it could detonate. The same element that Dr. Webb was carefully measuring into small doses to help Gerald sleep through the night was simultaneously being processed in secret facilities under military classification to build the most destructive devices ever constructed by human hands. The same substance. The same 3 protons. One version measured in milligrams in a cracked ledger in a psychiatric ward. The other version measured in tons in reinforced warehouses guarded around the clock. I want you to hold that image, because it captures something about this element that nothing else in its history does quite so clearly. To understand the military chapter, you need one piece of physics first, and I promise it is not complicated. Certain versions of this element, when struck by a fast-moving neutron, split apart in a way that releases an enormous amount of energy and produces a specific radioactive form of hydrogen as a byproduct. That radioactive hydrogen is the fuel that makes a thermonuclear device work. Without it, you have a powerful conventional weapon. With it, you have something in a completely different category of destructive force. The problem was that this radioactive hydrogen does not stay stable for long. It breaks down on its own over roughly 12 years. Which meant that any program trying to build and maintain a thermonuclear arsenal needed a continuous supply. And the only practical way to produce that supply at scale was to start with lithium. Not all lithium. This is where the story gets technically intricate in a way that had real human consequences. Natural lithium contains 2 versions of itself, 2 isotopes, present in fixed proportions. One of them is the one that produces the radioactive hydrogen when struck by a neutron. The other does not. The useful isotope makes up less than 8% of natural lithium. The rest is the other version. To make the weapons program work, you needed to take natural lithium and separate those two versions from each other, concentrating the rare one to extremely high purity. That process was called isotope separation, and it required enormous industrial infrastructure, enormous amounts of energy, and one additional material that turned out to be a serious problem: mercury. The separation method that both major powers settled on in that era relied on mercury cycling through the system as a chemical intermediary. Vast quantities of it, moving continuously through cascades of reaction chambers, doing the chemical work of pulling the two isotopes apart. The facilities that ran this process consumed mercury on a scale that is difficult to fully picture. And mercury does not stay where you put it. It migrates. It seeps into soil. It evaporates at room temperature and moves through ventilation systems. It finds its way into groundwater, and from there into rivers, and from there into everything downstream. The facilities that ran lithium isotope separation for decades left contamination in their surrounding environments that persisted long after the programs ended. At one major site, cleanup efforts were still ongoing well into the 21st century. The workers who operated those facilities in the early years did so without full knowledge of the risks they were accumulating in their own bodies. The communities near those sites paid a price that had no direct relationship to any decision they had made. This is the pattern that keeps appearing throughout the history of this element, in the medical crisis, in the mining story, and now here in the military chapter. The cost of progress lands on people who were not in the room when the decisions were made. The separation facilities ran for years. The stockpiles of concentrated isotope grew, and as they grew, something else grew alongside them: the leftover material. Every ton of concentrated useful isotope produced a much larger quantity of the other version, the one the weapons program did not need. That material was stored. There was no immediate use for it. It piled up in containers in warehouses, classified and secured and essentially forgotten, a byproduct of a program that was entirely focused on what it was trying to produce rather than what it was generating as waste. That forgotten material would eventually turn out to be extraordinarily valuable. But that realization came later, and we will get there. First, the geopolitics. Because while all of this was happening inside classified facilities, a completely different kind of race was developing on the surface of the Earth, in the soil and rock and ancient underground water of specific geographic regions that had no idea they were about to become strategically critical territory. Pull up a map of the world and look at the western interior of South America. There is a region of high-altitude plateau sitting between mountain ranges. A vast, elevated plain where the air is thin and the sun is punishing, and the landscape looks like something a set designer would build if they wanted to suggest another planet. The ground in much of this region is pale, almost white in places, crusted with mineral deposits laid down over millions of years by the slow evaporation of ancient water bodies. Beneath that crust, in pockets of liquid that have been concentrating for longer than modern human civilization has existed, is the largest accumulation of lithium on the surface of the Earth. 3 neighboring countries share this geological inheritance. Each of them has handled it differently, and those different approaches have produced very different outcomes in terms of who benefits and who absorbs the cost. The first country sitting on the largest single deposit moved slowly and defensively, resisting foreign corporate involvement for years, insisting on state-led development, building extraction infrastructure through a national company that ran into technical difficulties and funding gaps. Progress was real but slow. Then bilateral agreements opened the door to foreign partners and the pace changed. The extraction is now growing, but the gap between the potential of the deposit and the current output remains large, and the communities living near the extraction zones are watching the water table with an anxiety that has been building for years. The second country opened its doors to international investors early and aggressively. Companies from multiple continents arrived with capital and equipment and project timelines. Extraction scaled faster. Revenue came in. Local communities in the affected provinces filed formal objections, held protests, petitioned regional governments. Some of those protests achieved temporary pauses. None achieved permanent stops. The water that feeds small rivers and supports traditional farming in the high plateau is being consumed by the evaporation process at rates that the existing hydrology was not designed to sustain. The flamingos that nest in the shallow saline lakes of the region have been declining in certain areas. The correlation between extraction activity and those declines is visible in the data. Whether it rises to legal proof of causation depends on who is funding the study. The third country in this geological triangle has been the most cautious, not by principled choice necessarily, but by a combination of internal political complexity and the particular nature of its deposits, which are distributed across multiple provinces with different governance structures, making coordinated large-scale extraction more complicated to organize. But the interest is there. The investment is arriving. The pressure to extract faster is building from multiple directions simultaneously. And then there is Australia, which sits outside this triangle entirely, but has become the largest producer of lithium by raw volume through a completely different method. No evaporation ponds, no ancient brine, just hard rock mining in the conventional sense, open pits and heavy machinery and ore processing, extracting lithium from solid mineral deposits that are some of the richest in the world. The output goes primarily to processing facilities in East Asia, where the raw concentrate is refined into the battery-grade material that the global market actually needs. Australia mines it, someone else processes it, and then it travels again to wherever the batteries are being built. That chain, from mine to processor to manufacturer, spanning multiple countries and multiple ocean crossings, is the supply structure that the entire green energy transition currently depends on. And several major economies have looked at that chain and felt a very specific kind of dread. Because depending on a multi-stage international supply chain for a material you have declared strategically essential is a vulnerability. And vulnerabilities have a way of becoming crises when the geopolitical weather changes. The leftover material from the weapons program, the isotope that nobody wanted, the classified waste sitting in containers in guarded warehouses across 2 continents, turned out to be one of the most useful materials in the entire history of energy engineering. And the people who figured that out were not the ones who had produced it. They were a completely different generation of scientists working on a completely different problem, who looked at the stockpiles and realized that what the weapons program had discarded was exactly what they needed. Let me back up and explain how that happened, because the path from military waste to future energy material is not obvious, and it is genuinely one of the stranger reversals in the history of technology. When you run a thermonuclear weapons program and separate lithium into its 2 isotopes, you end up with large quantities of the version you did not need. That version, the heavier one, the one that makes up the vast majority of natural lithium, was stored because you cannot simply dump classified material and because someone, somewhere, assumed it might eventually be useful for something. That assumption turned out to be correct in ways nobody had anticipated. Engineers working on advanced reactor concepts needed a material that could carry enormous heat away from a reactor core without becoming dangerously radioactive in the process. The requirements were specific and demanding. The material had to remain liquid across a very wide temperature range. It had to conduct heat efficiently. It had to be chemically stable under sustained radiation exposure. It had to be light enough to move through pipes without requiring enormous pumping pressure. Most materials that meet some of those requirements fail on the others. The heavier lithium isotope met all of them with remarkable consistency. When you pump this material through a reactor system, it absorbs the heat from the core, carries it away to wherever you need it, gives up that heat to generate power, and returns to the core to absorb more. Under neutron bombardment, it does not transform into highly radioactive products the way most materials do. It stays manageable. It stays useful. The weapons program had spent enormous resources producing it as a byproduct and storing it as waste. And now it turned out to be close to ideal for one of the most technically demanding applications in all of energy engineering. There is something almost darkly funny about that reversal if you are willing to look at it from a distance. The same institutional logic that classified this material and locked it in warehouses also preserved it long enough for a different generation to recognize its value. If the waste had simply been discarded, as it might have been in a less security-conscious program, it would have been gone. Instead, the caution that came from secrecy accidentally preserved a resource that nobody yet knew was a resource. The application that has attracted the most attention in recent years is experimental fusion energy. There is a large international project being assembled in southern France, a collaboration involving dozens of countries pooling resources and expertise to build a device that can sustain a fusion reaction, the same fundamental process that powers the sun, long enough and stably enough to prove that it can be done as a practical energy source. This project has been under construction for years and is one of the most complex engineering undertakings in human history. At the heart of the design is a hollow chamber shaped roughly like a thick ring, inside which plasma, heated to temperatures far beyond the surface of the sun, is held in place by powerful magnetic fields. The fusion reactions happening inside that plasma release neutrons. Those neutrons have to go somewhere. And what they run into, the material sitting between the plasma chamber and the outer structure of the device, is a layer containing lithium, the heavier isotope, the old weapons waste. When the neutrons from the fusion reaction strike the lithium in that layer, they produce the very fuel that keeps the fusion reaction going. The device effectively breeds its own fuel from the neutrons that its own reactions produce. In a fully developed system, you would not need to bring in fusion fuel from outside. You would feed lithium into the outer layer, run the reaction, and the reaction itself would generate what it needs to keep running. The waste becomes the feedstock. The byproduct becomes the fuel source. The material that nobody wanted becomes the thing the whole system depends on. I spent a long time sitting with that particular loop when I first understood it fully. There is something in it that goes beyond clever engineering. It is almost a structural argument about how value moves through time. Something discarded in one era, treated as a burden, stored out of obligation rather than intention, becomes essential in another era for reasons that could not have been predicted when the storage decision was made. The value was always there. The context that revealed it had not yet arrived. Now here is where the story pulls in a direction that most people have never considered when they think about lithium. Because so far in this story, the element has appeared as a medical compound, a consumer product, a weapons material, an energy engineering tool, and a geopolitical flashpoint. But if you go looking in the right places, you find it doing things that are so ordinary, so embedded in the daily functioning of the physical world, that most people never register them at all. The machine in a factory that has been running continuously for 3 years without a breakdown. The one that stamps or cuts or assembles something thousands of times per hour. That machine has bearings. Inside those bearings is grease. And in all likelihood, that grease is a lithium compound, because lithium-based lubricants handle heat and pressure and moisture across a wider range of conditions than almost any alternative. Roughly 7 out of every 10 containers of industrial grease sold anywhere in the world contain lithium. That statistic sits quietly behind every piece of machinery that keeps the modern supply chain moving, every conveyor belt, every vehicle axle, every industrial hinge and rotating joint. You cannot see the lithium. You cannot smell it. But take it away, and the noise starts within hours, and the failures follow within days. The glass in the screen you use to read and watch and communicate has a different refractive quality than ordinary glass, a resistance to impact and thermal shock that ordinary glass does not have. In many cases, that quality comes from lithium oxide added during the glass-making process. It lowers the melting point of the mixture, which means less energy to produce it. It changes the molecular structure in ways that make the final product harder and more resistant to cracking. The glass that sits between your eyes and everything you look at on a screen may well contain this element, processed out of rock from the other side of the planet and incorporated so completely into the final product that it is invisible and odorless and entirely without obvious presence. The ceramic joint replacement inside someone's hip, the material that lets a person walk without pain for years after their own cartilage has failed, that ceramic may contain lithium compounds that were used in the firing process to achieve the exact density and hardness required for a medical implant. The person walking does not know. The surgeon who placed the implant may not have thought about it. The manufacturing specification that required it was written by engineers who were thinking about material properties and not about the geological journey that brought the raw compound to their facility. The submarine, running deep and silent, carries the crew inside a sealed metal hull where the air must be continuously managed because there is no outside to draw from. The chemical system that scrubs carbon dioxide from that recycled air and releases oxygen back into it has been using lithium compounds to do that job for decades. The crew breathes because of this element. Not metaphorically, literally. The lithium absorbs what they exhale and gives back what they need to keep breathing. Every watch, every meal, every hour of sleep in that sealed environment happens in air that lithium is continuously processing. The solar power plant in a dry and sunny region that generates electricity not just during daylight but through the night uses a thermal storage system at its core. Molten salt mixtures, some of which contain lithium compounds, absorb heat during the day at temperatures high enough to melt most metals, hold that heat through the evening, and release it overnight to drive turbines that generate electricity for thousands of homes. The homes go dark when the sun goes down in the public imagination. In reality, in places where this technology is deployed, the electrons keep flowing. And some portion of that continuous supply comes from lithium sitting at several hundred degrees in an insulated tank, quietly doing its job in the dark. I'm not listing these to impress you with the number of applications. I am listing them because they add up to something specific. This element is not a niche material used in specialized circumstances by specialized industries. It is woven into the texture of how the modern world physically functions, at the level of the machinery that makes things, the surfaces we touch, the air we breathe in sealed spaces, the light we see by after sunset. Remove it, and you do not lose a feature, you lose infrastructure. And that fact, that quiet pervasiveness, is exactly what makes the next question so loaded. Lithium will not save the planet. And anyone telling you otherwise is selling you something. That is not pessimism. That is the honest conclusion you arrive at when you actually look at the physics, the supply numbers, and the extraction reality we have been building through this entire story. Lithium is an extraordinary material. It is also a finite one, geographically concentrated, environmentally costly to extract, and physically limited in ways that no amount of engineering enthusiasm can fully engineer around. The question is not whether lithium is good or bad. The question is what it can actually do and what comes after it. Start with the physics, because the physics does not negotiate. The best lithium battery cells available right now store somewhere between 150 and 300 watt-hours of energy per kilogram of battery weight. That sounds impressive until you put it next to liquid fuel, which stores roughly 12,000 watt-hours per kilogram. Yes, an electric motor converts energy to motion far more efficiently than a combustion engine does. When you account for that difference, the practical gap narrows significantly. But it does not close. A fully charged lithium battery pack in the best electric vehicle currently available still carries the energy equivalent of a few liters of fuel in terms of what actually reaches the wheels. For a city commute, that is more than enough. For a fully loaded long-haul truck crossing a continent, or a cargo ship crossing an ocean, or a passenger jet crossing between continents, it is nowhere near enough and will not be for any time frame that current engineering can honestly project. This matters because the green transition conversation often treats lithium batteries as a universal solution, when they are actually a very good solution for a specific range of applications and a poor solution for others. Acknowledging that boundary is not defeatism. It is the prerequisite for finding the right tools for the applications where lithium genuinely cannot reach. Now the supply question. Global reserves of lithium are estimated at tens of millions of tons, with additional potential resources that could push that figure much higher as exploration continues. At current consumption rates, that sounds comfortable. But consumption is not staying at current rates. The number of lithium battery cells being produced each year is growing at a pace that makes linear projections almost useless. Every year the electric vehicle market expands. Every year more grid-scale energy storage is installed. Every year more consumer electronics are sold. The demand curve is not a straight line. It is accelerating. When you map that acceleration against known reserves and factor in the geographic concentration of those reserves in a small number of countries, the picture that emerges is not one of comfortable abundance. It is one of a material that will become progressively more contested, more expensive, and more politically fraught as the decade advances. The price spike that sent markets into chaos a few years ago, when the cost per ton multiplied several times over in less than 2 years before crashing back down, was not an anomaly. It was a preview. Raw material markets behave that way when demand grows faster than supply infrastructure can respond, and the lithium market has every structural condition necessary to repeat that cycle, probably more than once. So what is actually being built to address this? Several things simultaneously, at different stages of readiness. And the honest answer is that none of them is complete yet, but all of them are real. Sodium-ion batteries are already in commercial vehicles. The chemistry is less energy-dense than lithium-ion, which means a larger and heavier battery for the same range, but sodium is one of the most abundant elements on Earth, available essentially everywhere, with no geographic concentration and no geopolitical sensitivity. For urban vehicles with predictable short daily routes, the energy density penalty is manageable. These batteries will not replace lithium in high-performance applications. They will absorb a portion of the mass market demand that would otherwise put additional pressure on lithium supply, which buys time for the harder technical problems to be solved. Solid-state lithium batteries are the next significant leap for performance applications. Replace the liquid electrolyte inside a conventional lithium cell with a solid ceramic or glass material, and several things improve simultaneously. The energy density increases because you can use a lithium metal anode instead of a graphite one, and lithium metal holds roughly 6 times more charge per unit of volume. The safety improves because a solid electrolyte does not burn the way liquid electrolyte does. The longevity improves because the degradation mechanisms that shorten conventional cell life are reduced. Multiple major manufacturers are in late-stage development. The first commercial solid-state cells are expected to reach vehicles within the next few years. When they do, the performance gap between electric and combustion vehicles narrows further, and the argument for electrification in applications that are currently marginal becomes substantially stronger. Recycling is where the most immediate and most underutilized opportunity sits. Right now, only a small fraction of lithium batteries reaching end of life are being properly recycled and the lithium recovered. The rest goes to landfill or is processed in ways that recover cobalt and nickel, which are worth more per ton, while the lithium is lost. This is economically rational given current lithium prices and technically unnecessary given that the recovery methods exist. Legislation in several major markets is already changing the economic calculation by requiring minimum percentages of recycled content in new batteries. Processing facilities are being built. The infrastructure is developing. Within a decade, the recycling stream will be a meaningful contributor to supply in a way it currently is not. And unlike mined lithium, recycled lithium comes without new evaporation ponds, without new open pits, without new communities watching their water disappear. The geothermal route is the one that gets the least attention and may have the most interesting long-term potential in certain regions. Underground hot water sources in parts of Europe contain lithium concentrations that are modest compared to the best South American brines, but significant compared to ordinary groundwater. Some of these sources are already being tapped for geothermal energy, where the water is pumped up, its heat is extracted to generate electricity, and then the water is pumped back down. Adding a lithium extraction step between the heat exchange and the reinjection requires additional equipment but no additional surface disturbance, no evaporation ponds, no new water consumption. The water goes back where it came from, minus the lithium that was dissolved in it. Pilot installations are already running. If they demonstrate the economics work at scale, Europe gains a domestic lithium source that requires no new mines in the conventional sense. None of these paths is fast enough on its own. All of them together might be. And now I want to close this story the way it deserves to be closed. Not with a technology forecast, with an honest accounting. We started at the very beginning of the universe with an element that formed in the first few minutes of existence and drifted through billions of years of cosmic time before landing in rock on a specific planet. We followed it into a cold northern laboratory where a young assistant noticed something that did not fit his categories. We watched it go into soda bottles and grocery store shelves and psychiatry wards and classified military facilities and open-pit mines and submarine air systems and the wings of commercial aircraft and the screens of devices that now sit in the pockets of billions of people. At every single stage of that journey, the element itself remained exactly what it was. 3 protons, 1 available electron. The same physical reality it had been in the first minutes after the universe began. What changed every single time was us. Our understanding of what we had found, our decisions about what to do with it, our willingness or unwillingness to look honestly at the cost of those decisions and acknowledge who was being asked to carry that cost. The people who paid for the grocery store disaster were patients who trusted a product on a shelf. The workers in the isotope separation facilities paid with their long-term health. The communities near the evaporation ponds are paying now with their water. The flamingos are paying with their habitat. The bill for progress is always real, and it is always paid by someone. And the pattern that runs through this entire story is that the people making the decisions and the people absorbing the consequences are almost never the same people. That is not an argument against progress. Progress brought Gerald home from a psychiatric facility he had been living in for years and gave him back a decade of ordinary life. Progress put a battery in a device that changed how billions of people communicate and learn and connect. Progress is building the infrastructure for energy systems that could meaningfully reduce how much the atmosphere warms over the coming decades. These things are real and they matter. But progress without honesty about cost is not really progress. It is just the transfer of a burden from people with choices to people without them. And the history of this one element, traced from the Big Bang to the inside of your phone, is one long demonstration of exactly that pattern playing out again and again across different eras and different contexts and different groups of people who never got to vote on what was being decided. Here is the question I want to leave you with, and I want you to sit with it honestly before you answer. If the green energy transition we are currently building requires us to drain the water from communities that have lived in those highlands for thousands of years, if it requires us to accept that certain ecosystems will be permanently altered so that wealthier countries can charge their vehicles overnight, is that a transition we are comfortable calling clean? Write your answer in the comments. I am genuinely asking. If this story made you think differently about something you thought you already understood, subscribe and leave a like. It is the clearest signal that this kind of deep storytelling is worth continuing. We have more elements to go, and the next one has a history that is just as strange and just as human as this one.